Thank you, Dr. Ashworth. Good morning. My name is Christian Melgar, and I'm the design team lead for Air Combat Engineering Solutions. I'd like to welcome the members of the panel and audience to the final design presentation for the fighter-interceptor named the Vindicator. For the remainder of today's presentation, the screen above me will be referred to as the primary screen, and the screen to your right will be referred to as the secondary screen. The Vindicator has a forward-swept and closed-couple canard configuration with dual vertical tails. Its two F-135 engines allow it to sustain a 9G maneuver at sea level and supercruise to a combat radius of 200 nautical miles at Mach 1.3. The primary screen now shows the initial CAD rendering of the Vindicator's design, while the secondary screen shows the 32nd scale wind tunnel model with tough supply that was used during our testing. I would now like to take a brief moment to introduce the team that engineered the Vindicator's design, starting with Zachary Spar, Alec Denslow, Parker Phillips, Michael Apfelzweig, Jason Ruiz, Brittany Pfeiffer-Ryder, Andrew Bolduck, Jonathan Swisgood, and Spencer Holmes. The primary screen now shows an overview of today's briefing, including the necessary requirements to successfully accomplish the mission, followed by the aircraft description and configuration. We will then continue with the structural analysis that was conducted to verify the aircraft's ability to sustain a 9G maneuver at sea level. This is followed by the initial wind tunnel results that were used to verify our predicted performance characteristics, as well as the modifications that were implemented to the final wind tunnel test configuration. We will finish today with conclusions and recommendations needed to move forward with further RDT&E phases. I would now like to introduce up to the stage Zachary Spar.
Thank you, Christian. I'm going to be covering the motivation and design requirements behind the Vindicator. The United States has demonstrated a clear need for a new fighter-interceptor aircraft. Currently, the Air Force is using F-22s and the Navy is using F/A-18s to fulfill an interceptor role. The F-22 is in short supply, and it cannot take off and land from an aircraft carrier, which limits its versatility in response to incoming threats. And the F/A-18 is incapable of supercruise, which limits its response speed. With the rising tensions around the world, especially with North Korea's recent weapons testing in direct violation of the Nuclear Non-Proliferation Treaty, the United States should not be forced to choose between response speed and response versatility when reacting to incoming threats. The secondary screen shows a map of potential staging locations in East Asia. The two air bases are Osan and Misawa, as well as two potential staging locations for aircraft carriers. The blue circles indicate a 200 nautical mile combat radius, which is the area that the Vindicator will effectively be able to defend. By staging at these locations, the Vindicator is capable of defending from threats coming from locations such as North Korea, China, and Russia. The primary screen now shows the mission profile for the Vindicator. It will begin by taking off and climbing to its height of 40,000 feet, where it will supercruise to its combat radius of 200 nautical miles. At this point, it will perform a 20-minute combat air patrol, followed by a 5-minute engagement, which consists of 3 minutes of military power and 2 minutes of full afterburner. After successfully defeating its enemies in the engagement, the Vindicator will perform a secondary subsonic cruise, either to its initial or to a secondary base, where it will descend and land. The RFP requirements are outlined on the primary screen. The three most constraining requirements were the ability to take off and land from both an 8,000-foot runway and an aircraft carrier with the same configuration, the ability to supercruise at a speed of Mach 1.2 or greater, and the ability to sustain a 9G maneuver at sea level. The additional requirements outlined by the Navy and Air Force are shown on the secondary screen. The Navy's requirements are mainly sizing to be able to fit on the aircraft carrier elevator, as well as load requirements to be able to sustain those experienced during landing and takeoff. The Air Force's requirements specify the ability to take off with an obstacle at the end of a runway, as well as an overall fuel requirement. The primary screen now shows the design space for the Vindicator. The two most constraining factors were the ability to sustain a 9G maneuver at sea level, as well as to be able to take off from an aircraft carrier. With its design point located at a wing loading of 83 pounds per square foot and a thrust to weight ratio of 1.2, the Vindicator is capable of meeting all design requirements. I would now like to introduce Alec Denslow.
Thank you, Zachary. I will be discussing the aircraft configuration and layout. Shown on both the primary and secondary screens is an isometric and 3 view of the Vindicator. Its most notable feature is its negative 30-degree leading edge sweep, which defines the forward swept design. Because the Vindicator does not employ the use of horizontal tails, close-coupled all-moving canards are used to control pitch authority, and dual 75% all-moving vertical tails are used to control yaw authority, especially in the event of a one-engine-out scenario. The cockpit was optimized for pilot field of view, with a down view over the nose of 16 degrees and a side lateral view of 50 degrees, as well as an unobstructed view over the top of the canopy. The cockpit was also optimized for pilot comfort during high G loading, such as those sustained during the 9G maneuver at sea level. And this was accomplished with a seat back angle of 25 degrees. Shown on the secondary screen are the internal weapons stores. The Vindicator carries 2 heat-seeking and 2 radar-guided missiles, as well as a 20mm gun with 200 rounds of ammunition. The overall length of the fuselage of the Vindicator is 65 feet, and the wingspan is 57 feet, and a fuselage diameter of 12 feet was used to house the 2 Pratt & Whitney F-135 engines, pictured on the secondary screen. The forward 12% of the fuselage is used to house the radome, while the mid-22 section of the fuselage is used to house the cockpit, avionics, and stowage for the nose landing gear, while the aft 66% of the fuselage is used to house the engines, fuel, armament, and stowage for the main landing gear. The Vindicator employs the use of retractable tricycle landing gear. The main gear is a single wheel configuration, while the nose gear is a twin wheel configuration as per Navy specifications. Included is a tailhook that is 72 inches long for resting on an aircraft carrier. The landing gear locations are shown on the secondary screen, referenced to the center of gravity. The lateral ground clearance criteria is satisfied at an angle of 11.3 degrees, which is greater than the required 5 degrees. And the lateral tip-over criteria is also satisfied at an angle of 51.7 degrees, which is less than the required 55 degrees. Finally, the longitudinal ground clearance or tail strike criteria is satisfied at an angle of 16 degrees. I would now like to introduce Parker Phillips.
Thank you, Alec. I will be discussing the structural design and analysis performed on the Vindicator. On the primary screen is a VN diagram, which was used to determine the critical load condition experienced by the Vindicator. This diagram includes a flight envelope at sea level, as well as the most constraining gust line, which is the rough air gust. Only the most constraining gust line is shown, as the highest load experienced during the gust is well within the boundary of the 9G maneuver experience. Therefore, the critical condition was determined to be the 9G maneuver. On the secondary screen are the materials used in the construction of the Vindicator structure. Titanium is utilized for high loading components such as wing spars and bulkheads within the fuselage. Additionally, aluminum is used for less load-bearing components such as longerons, shapers, and frames, as well as the skin over the empennage and fuselage. Finally, carbon fiber is utilized for the wing skin, as this allows for the implementation of aeroelastic tailoring effects. On the primary screen is a structural ghost view of the empennage, or of the wings. The wing utilizes a 2-spar design in order to allow for a higher skin loading to increase the effects of aeroelastic tailoring. These spars are located at 12% of the chord and 65% of the chord. Additionally, internal fuel tanks are located in the strakes and in between the spars up to 2/3 span. Trailing edge flaps are located on the inboard portion of the trailing edge of the wing, and ailerons are located on the outboard portion of the trailing edge of the wing. Shown on the secondary screen is a structural ghost view of the empennage. Both the canard and vertical tails utilize a single spar design. This aluminum spar allows for the implementation of the all-moving, allows for the all-moving configuration of both the canard and vertical tails. On the primary screen is a structural ghost view of the fuselage. Titanium bulkheads are located forward and aft of the cockpit, as well as utilized for the mounting of the engines. Internal fuel tanks are located around the engines in the aft of the plane, as well as in the mid portion of the plane around the ducts and weapons bay. Aluminum longeron shapers and frames are utilized to maintain the shape of the aluminum skin. And shown on the secondary screen is the structural ghost view of the entire aircraft. In order to analyze the structures for the Vindicator, hand calculations were initially performed using Schrank's and general bending theory. These utilize the material properties for the different components of the wing and canard in order to determine the size of the spar caps and thickness of the skin. And this was followed up with an ANSYS model in order to confirm the hand calculations and validate the design. Shown on the primary screen is the ANSYS model for the wing box under bending stress, and shown on the secondary screen are the primary stress components or stresses analyzed for the wing box. Most notably, the forward spar bending stress is at 128 KSI, while the material property allows for 130 KSI. This identifies that the forward spar bending stress is the primary motive failure for the wing box. Shown on the primary screen is the canard spar. Due to the single spar design, only the canard was analyzed. And shown on the secondary screen is the stresses determined from the ANSYS calculation, which identified that the spar shear is the primary motive failure for the canard spar. Now I'd like to introduce Michael Alphazwag.
Thank you, Parker. I'll be discussing the design and assembly of the Vindicator wind tunnel model, which was used to verify the performance metrics determined in preliminary design. In order to size the wind tunnel model, A.C.E.S opted to go with the largest scale that would meet the 5 metrics shown on the primary screen. The wind tunnel test section constrained the model to minimize solid blockage and wall effects. Furthermore, the model could produce no more than 40 pounds of lift to avoid overloading the balance. The $500 budget allowed for material costs, limited the 3D print material to 84.6 cubic inches, and the most constraining factor, shown in bold, is that the internal structure could not tear out through the A.B.S printed plastic. The secondary screen shows the 1/32 scale rendering of the model with the major dimensions shown. The 3D printed parts were divided into 12 pieces. These pieces interlock together with tabs, or would use the internal structure for mounting. The secondary screen identifies these parts as well as their individual or collective print volumes. The parts were printed on a Stratasys 1200 ES fused deposition molding printer. This printer formed ABS plastic parts and automatically incorporated a support structure which simplified the printing process. All the parts were printed in one print job, which took about 120 hours. The photo inset on the primary screen shows the printing progress after 72 hours. And the secondary screen shows the parts being test fitted prior to final assembly after being sanded and prepared for painting. An internal structure was required to withstand the test loading in the wind tunnel. The internal structure also had to allow for the wings and empennage to be completely removable from the model to test individual contributions of these components. The internal structure also could not penetrate into the free stream and was also designed to not encroach upon the inlets of the model to reduce drag. The secondary screen shows the identification numbers of these parts as well as how they were fabricated. All the parts were made out of steel. I'll now demonstrate the assembly of the wind tunnel model with the following video. First, the wing channel U-bracket and wing balance mount are welded to the spine. After this, the fuselage midsection is slid into place, and the fit is checked with the wing U-bracket. Next, the fuselage aft, forward, and nose sections are brought into place and epoxied together permanently. Moving to the right side of the model, the right canard with its spar already glued in is slid into place. The left canard is then slid on the other side, and the canards are fastened with a single pin through the top. Now moving to the midsection of the model, the wing spars are inserted into the top of their respective channels and dropped into place. To prevent the spars from backing out, locking plates are then inserted. The outer portion of the wing had an internally glued hex nut and then had a joining rod which aligned it with the strake. The wing and strake were glued together after being aligned, and the strake has its own alignment pin which corresponds to a hole in the side of the fuselage. The wing and strake assembly is then carefully placed onto the spar and slid into place so that they fit into the fuselage. And the wing is held in place with a single countersunk screw through the bottom. Moving now to the aft section of the model, the vertical tails already have the support structure glued in, and they are inserted into a press fitting at the aft section of the fuselage. And this fly-through view shows that the internal structure does not penetrate into the inlets, and concludes with an isometric view of the model. And the secondary screen is a photo of the initial model with tufts applied after being painted prior to its initial test. I would now like to introduce Jason Ruiz.
Thank you, Michael. I will now go over the wind tunnel test design. In order to verify the Vindicator's performance characteristics, wind tunnel testing needed to be conducted. The wind tunnel used was an AeroLab 87 series closed circuit wind tunnel. The wind tunnel houses a 32-inch by 45-inch test section which provides adequate room for the Vindicator test model. The wind tunnel is also equipped with a 6-axis perimeter balance capable of holding a 40-pound load, as well as providing a range of angle of attacks and side slip angles which can be seen on the primary screen. The secondary screen displays a diagram of a closed circuit wind tunnel, as well as a picture of the test section used. In order to compare our data, 5 performance coefficients needed to be collected. The coefficients, as seen on the primary screen, are the lift and drag force coefficients, as well as the pitch, roll, and yaw moment coefficients. A.C.E.S also decided to test 3 different configurations in order to analyze the individual contributions made by individual components. The three tested configurations can be seen on the secondary screen. Additionally, A.C.E.S also decided to collect flow visualization pictures in order to analyze any differences between the predicted and the experimental data. A tear test was also conducted in order to remove any forces and moments caused by the balance itself. I would now like to introduce Brittany Pfeiffer-Ryder.
Thank you, Jason. I'll now go over the initial wind tunnel testing results. 5 wind tunnel tests were performed. The first was an aeroelastic test. This was done in order to determine the speed that the wind tunnel would be ran at for all of the wind tunnel tests. This was conducted by mounting the model to the balance and setting the balance to an angle of attack of 26 degrees. Then, the velocity of the wind tunnel was slowly increased until flutter occurred. It was determined that the wind tunnel would be ran at 92 feet per second for all of the wind tunnel testing. The next 3 tests tested the 3 model configurations. Each configuration had an alpha range and beta sweep test performed. The alpha range test tested angles of attack from -4 to 26 degrees in 2-degree increments, and the beta sweep test tested side slip angles from 0 to 10 degrees in 2-degree increments. Finally, a tear test was done in order to analyze the balance's contribution to the force and moment coefficients so it could be subtracted from the rest of the wind tunnel data. This was done by running the wind tunnel at the test velocity without the model mounted to the balance. The secondary screen shows a screenshot of the AeroLab program with the input parameters entered. I'd like to note that the parameters are entered in SI units because that is what the program references. Flow visualization was captured during testing. The primary screen shows pictures of the canard and wing at -4, 12, and 26 degrees angle of attack. As the angle of attack increased, the flow separated at the root of the wing and moved out towards the tip. This is an expected characteristic for forward swept wings. At high angles of attack, the flow reattached at the root of the wing because of the downwash produced off the canards. The secondary screen shows flow visualization for the vertical tails at -4, 12, and 26 degrees angle of attack. At high angles of attack, yaw authority was lost because of the fuselage blocking the free stream flow. From the force and moment coefficients gathered during wind tunnel testing, performance plots were created. The first is a seal versus alpha plot shown on the primary screen. This plot compares the predicted and 3 model configuration data, where the predicted data has a maximum C sub L of 1.71 at a stall angle of attack of 17 degrees. The full configuration experimental data has a maximum C sub L of 1.71 at 26 degrees angle of attack. The shift in angle of attack is because of the lift produced off the fuselage and the forward swept wing configuration. If the balance could reach higher angles of attack, it is anticipated that the CL value would continue to increase until stall occurred. The primary screen shows a CD versus CL plot. From this plot, the CD naught value can be obtained that is used in performance calculations. The secondary screen shows CD naught values for each configuration, where the experimental full configuration has the highest CD naught value. The primary screen shows a drag versus velocity plot that compares the total drag for the predicted and experimental data. The experimental full configuration data is 193% greater than initially predicted. This increase in drag is due to the flow-through nacelles of the model, as well as the wingtip vortices and vortices off the nose of the model. The secondary screen shows drag values at a minimum drag velocity of 198 knots. The primary screen shows a thrust available thrust required plot at sea level. From this plot, it is shown that the maximum mill thrust velocity has shifted from Mach 1.3 to Mach 9 from predicted to experimental data. The shift in thrust required is due to the increase in drag for the experimental data. The secondary screen shows the 9G maneuver at sea level. The red dashed line shows that the Vindicator is capable of completing a sustained 9G maneuver at sea level with the use of afterburners. This satisfies the RFP requirement. The primary screen shows a thrust available thrust required plot at 20,000 feet. This is the mid-altitude for the maximum performance climb. At this altitude, the Vindicator has a max thrust available velocity of Mach 1. This is decreased from the predicted Mach 1.7. The secondary screen shows a thrust available thrust required plot at 40,000 feet. This is the altitude where the supercruise portion of flight will take place. The red dashed line shows that at this altitude, the Vindicator is capable of supercruising at Mach 1.35. This is greater than the required Mach 1.2, so the Vindicator satisfies the RFP requirement. On the primary screen is the predicted specific excess power plot. From this plot, it shows that the Vindicator has an absolute ceiling of 70,000 feet, although it will have an operating ceiling of 50,000 feet. The secondary screen shows the experimental specific excess power plot that has the same absolute and operating ceiling. From this plot, the velocities for the max performance climb can be obtained, and the bubble between the 5,000 and 10,000 foot per minute line is due to the wave drag that occurs going through Mach 1. The primary screen shows the predicted flight envelope that has a maximum G loading of 9 Gs and a minimum G loading of -3 Gs at a 9G maneuver corner velocity of 320 knots and a Q limit of 850 knots. The secondary screen shows the experimental flight envelope, which has the same upper and lower G limits, although the corner velocity has decreased to 306 knots and the Q limit has decreased to 600 knots. This decrease is due to the change in thrust required from predicted to experimental. I would now like to introduce Andrew Bolduck.
Thank you, Brittany. I'll now be covering the stability results and some performance characteristics drawn from the first set of wind tunnel testing. The primary screen displays the pitch moment diagram, which shows pitching moment versus angle of attack. This plot shows that the Vindicator was predicted to be unstable in pitch due to the forward swept wing and close couple canard configuration. However, this is acceptable for a fighter aircraft to maintain maneuverability. Experimental testing was able to verify that the Vindicator still maintains its pitch instability. And the secondary screen displays key values that were drawn from this plot, where the most notable features is the positive slope for predicted and experimental data. The primary screen now displays the roll moment diagram, which shows rolling moment versus side slip angle. This plot shows that the Vindicator was predicted to be stable in roll with a negative slope, and experimental testing was able to verify that the Vindicator still maintains its roll stability. The secondary screen displays key values that were drawn from this plot, where the most notable features is the negative slope for predicted and experimental data. The primary screen now displays the yaw moment diagram, which shows yaw moment versus side slip angle. This plot shows that the Vindicator was predicted to be stable in yaw with a positive slope, and experimental testing was able to verify that the Vindicator still maintained its yaw stability. The secondary screen displays key values that were drawn from this plot, where the most notable features is the positive slope for predicted and experimental data. The primary screen displays a pitch performance characteristic, where from experimental testing, A.C.E.S has determined that the Vindicator is 35% unstable in pitch, largely due to the negative static margin, as well as the unpredictability of the fuselage contributions during the experimental testing. Although an instability is desired for an aircraft to maintain maneuverability, A.C.E.S would like to reduce this instability to a value that closely matches similar aircraft. The secondary screen displays a yaw performance characteristic, where from flow visualization, A.C.E.S has determined that the vertical tails lost authority at high angles of attack. This is due to the fuselage blocking out the tails from free stream air, and A.C.E.S would like to improve this characteristic. I would now like to introduce Jonathan Swisgood.
Thank you, Andrew. I will be discussing the model changes in the second set of wind tunnel testing. The single, most effective, and simplest change that could be made to the aircraft to increase the pitch stability would be to move the wing aft on the fuselage. Shown on the primary screen is a continuum rendering of a modified wing on the left side with the wing moved aft compared to the original wing on the right. To make this change, a new wing spar had to be fabricated so that the original attachment points to the fuselage could remain the same. This refabricated wing spar ended up being the constraining factor as to how far aft the wing could be moved on the model. It resulted in a 0.9-inch shift on the model. Shown on the primary screen is the comparison of the modified spar with the original spar. The second change that had to be made in order to move the wing aft was the leading edge extensions had to be enlarged. On the secondary screen is a comparison of the modified leading edge extensions with the originals. By enlarging the leading edge extensions, the same attachment points on the 3D printed model were able to be maintained with the fuselage. A.C.E.S also decided to increase the size of the vertical tails by as much as possible so that more yaw authority could be maintained. To do this, and to also maintain the original height of the aircraft so the aircraft could still fit inside of an aircraft carrier elevator, the cant on the vertical tails was increased to 30 degrees from the original 15 degrees. By increasing this cant, the vertical tails were able to be scaled up by 11% while still maintaining the original aircraft height. To make this change to the vertical tails, new vertical tail spars had to be fabricated and then bent by an additional 15 degrees. Once the new vertical tails and vertical tail spars were installed on the original fuselage, any gaps between the fuselage and the vertical tails were filled in with modeling putty. A.C.E.S decided to test 3 different configurations for the second set of wind tunnel testing. Those configurations are one with the modified wings, one with the modified vertical tails, and one with both modifications on the aircraft. A.C.E.S used the same procedures for the second set of wind tunnel testings as was used in the original set of wind tunnel testing. Terra testing was also redone. On the secondary screen are pictures of the 3 different modified aircraft that were used in the second set of wind tunnel testing. On the primary screen now is a flow visualization picture of the aircraft with both modifications installed at an angle of attack of 26 degrees. A.C.E.S noted that even with the wing moved aft, the close coupled canard effect was maintained. Now on the secondary screen are flow visualization pictures of the vertical tail and the nose at the same angle of attack. A.C.E.S noted that the vertical tails still did lose yaw authority at those high angles of attack, and also vortices off the nose were noticed. Now I'd like to introduce Spencer Harms.
Thank you, Jonathan. I'll be covering the performance verification drive from the second set of wind tunnel testing. On the primary screen is a lift curve comparison plot showing all the configurations tested during the second set of wind tunnel testing, along with the original wind tunnel model and the predicted data. It was predicted that the Vindicator would have a maximum coefficient of lift of 1.71. This was verified during the second set of wind tunnel testing. During the second set of wind tunnel testing with both modifications implemented on the Vindicator, the lift increased to a maximum coefficient of lift of 1.78. Additional values can be seen on the secondary screen for all the remaining configurations. On the primary screen is a pitch comparison plot showing all the configurations as well as the predicted data. It was predicted that the Vindicator was 8% unstable. During the first set of wind tunnel tests, this was increased to 35% unstable. During the second set of wind tunnel tests, it was the pitch decreased in instability to a 27% unstable. Additional performance numbers are seen on the secondary screen. On the primary screen is a roll comparison plot showing all the configurations as well as predicted data. For a stable roll, it is warranted that the slope be negative. All configurations as well as predicted are stable in roll. For a fighter aircraft to be maneuverable, it is warranted that the aircraft not be overly stable in roll. The Vindicator is just barely stable in roll, thus is still able to remain maneuverable. On the secondary screen is additional data for the roll comparison plot. On the primary screen is the yaw comparison plot. For a stable yaw, it is warranted that the slope be positive. For all configurations as well as the predicted data, the slope is positive. It's similar to roll, it is not warranted for an aircraft to be overly stable in yaw. With the Vindicator just being stable in yaw, it is still able to be maneuverable. And as before, there's remaining numbers taken from this plot are seen on the secondary screen. On the primary screen is thrust available, thrust required plot at sea level. For all altitudes, the thrust required for the second set wind tunnel match the original wind tunnel data, so they are overlapping. At sea level, the maximum velocity achieved with mill thrust is at Mach 0.9, and with afterburners engaged, the Vindicator has a maximum velocity of Mach 1.0. The secondary screen is a thrust available, thrust required plot at sea level for the 9G maneuver. A.C.E.S had predicted that the Vindicator would be able to perform the 9G maneuver with mill thrust. However, during the second set wind tunnel test and the first set wind tunnel test, it was found that the Vindicator would require full afterburner to be able to perform the maneuver. On the primary screen is a thrust available, thrust required plot at 20,000 feet. The maximum speed achieved with mill thrust is at Mach 1.0, and the maximum speed with full afterburner is at Mach 1.3. On the secondary screen is a thrust available, thrust required plot at 40,000 feet. This is where the Vindicator will be performing its supercruise out to its 200 nautical mile radius. The Vindicator is able to supercruise at a velocity of Mach 1.35. On the primary screen is a modified experimental specific excess power plot showing lines of specific excess power. During the second set wind tunnel test, it was found that the absolute ceiling of the Vindicator was at 70,000 feet, which verified the predicted data on the secondary screen. The Vindicator has a maximum operating altitude of 50,000 feet, which again verified the predicted data on the secondary screen. On the primary screen is the modified experimental flight envelope. At sea level, the 1G stall is at 105 knots. When compared to the predicted data on the secondary screen, the 1G was at 106 knots. The 9G corner velocity for the experimental data was at 305 knots. When compared to the predicted data on the secondary screen, the Vindicator had a predicted 9G corner velocity of 320 knots. On the primary screen is the performance criteria. The Vindicator must be able to take off and land from an 8,000-foot runway. The Vindicator is able to do this with a takeoff distance of 1,471 feet and a landing distance of 2,703 feet. Also, the Vindicator must be able to take off and land from an aircraft carrier. To be able to achieve this, the catapult has a max load for the required takeoff velocity of 145 knots with a 53,000 pound load. The Vindicator is exactly 53,000 pounds for its gross takeoff weight. Thus, it's able to be able to launch from the aircraft carrier. To be able to land on the aircraft carrier, the arresting wire has an engagement velocity of 150 knots. The Vindicator has a touchdown velocity calculated to be 137 knots with the experimental data. Thus, it's able to meet the performance criteria. The Vindicator must also be able to supercruise at Mach 1.2 or greater at 40,000 feet. The Vindicator achieves this with a maximum supercruise velocity of Mach 1.35 at 40,000 feet. On the secondary screen is additional performance criteria. The most notable is the 9G maneuver at sea level. The Vindicator is able to still perform the 9G maneuver at sea level with the use of afterburners. On the primary and secondary screen are a 3-view and an isometric view of the final design, with both modifications implemented on the Vindicator. And now I'd like to welcome back Christian Melgar.
Thank you, Spencer. I would now like to continue with the market analysis and life cycle cost analysis for the Vindicator. The primary screen now shows key performance characteristics of similar aircraft. While the FA-18, F-22, and F-35 all implement advanced technologies, none of them are able to accomplish each of the mission requirements, while the Vindicator is able to accomplish all of them. The secondary screen now shows a life cycle cost analysis for the Vindicator. It was assumed that 368 operational aircraft would be produced, allowing for 20 squadrons of 18 aircraft each. This would provide both the Navy and the Air Force with 10 squadrons, along with 6 flight test articles. With a 25-year lifespan and 1% disposal cost, this allowed for the program estimate to be approximately $30 billion. Acquisition costs for each aircraft resulted in a unit price of approximately $81 million. I would now like to continue with the cost estimation for the model, along with the labor hours worked by the team. The primary screen shows the model cost breakdown for both the original and modified configuration, along with its structural components. For the model production, an overall cost of $482 was achieved in the RDT&E phases for the Vindicator. The primary screen now shows the labor hours worked by the team. The solid black line indicates the predicted hours worked, while the red line indicates the actual hours worked by the team. It was assumed that for every hour spent in class, each team member would contribute 2 hours outside of class. This allowed for an overall contribution of team of about 150 hours per week. To date, A.C.E.S has spent 1,952 hours on the Vindicator project. This is just 0.1% over the estimated 1,950. The secondary screen now shows each of the 5 job categories, split up into groups with the incurred cost for each job respectively. To date, A.C.E.S has accumulated a cost of approximately $97,000 for the RDT&E phases. The primary screen now shows a breakdown of those hours worked. An important thing to know from this chart is that the engineering and professional development accumulated the most time worked by the team, while the secondary screen shows a breakdown of those costs, of the cost for those hours worked. An important thing to note from this chart is that engineering and engineering management showed the largest increase in percentages due to the larger costs associated with those job categories. And I would now like to continue with the conclusions and recommendations from our analysis. The primary screen now shows conclusions gathered from both our wind tunnel and structural analysis. First, through the experimental wind tunnel data that was collected, A.C.E.S was able to verify the predicted performance characteristics and confirm that the Vindicator maintains the ability to successfully accomplish all of its mission requirements. Likewise, the structural analysis that was conducted on both the wing and canard verified the Vindicator's ability to sustain a 9G maneuver at sea level. Flow visualization that was used during wind tunnel testing allowed for the confirmation of key performance characteristics of forward swept wing design, where the wing root will stall first and the stall characteristics progress outwards towards the tip. The flow visualization indicated that once the wing root stalled at high angles of attack, the downwash produced from the canard allowed for the wing root to reattach, while the wing tip maintained attached flow. This indicates that the Vindicator is able to maintain flight characteristics at angles of attack higher than 26 degrees, although the limitations of the balance did not allow for those angles to be analyzed. This was confirmed by the experimental data as no stall angle of attack was observed. Last, the modifications to both the vertical tail and wing allowed for the improvement of performance characteristics to the aircraft, while the wing change allowed for the reduction of instability and pitch from 35 to 27% instability, which is within a more manageable range. Likewise, the vertical tail allowed for significant yaw stability improvement, especially at high angles of attack, although at the highest angles of attack, the yaw stability was decreased due to the block of flow from the fuselage. We'd now like to cover the recommendations from our analysis. First, the A.C.E.S would like to implement the changes to the vertical tail by increasing the angle from 15 to 30 degrees and increasing the size by 11% as the yaw stability was improved. Likewise, the implementation of the wing changes, as it significantly reduced the instability and pitch by moving the overall wing aft of the nose 2.4 feet on the full-scale aircraft. With both of these implementations, A.C.E.S recommends the production of the first flight test article to further verify our design. This now concludes our presentation. I'd like to thank all of you for your attention, and I will now field any questions from the panel and the audience.
I remember that. While they're getting situated up here, since we do have different panel members this time, I would ask that as they start their questions, they introduce themselves and let us know where you're from.
Hi, my name is Robert Anderson. I work at Raytheon Missile Systems. I guess I design bad things.
No, they're good things. They just shoot at bad people.
So currently I'm the Missile Integrated Product Team Lead on a program called Long Range Precision Fires. So it's a hypersonic airframe, ground-to-ground Army program. Great job, well organized. Everybody presented really well. So thanks for coming prepared. I'm just going to limit it to one question, one comment, so there's plenty of time for the other panels. It looked like you had some longitudinal fuel tanks in the fuselage. Do you have any concern about your pitch stability as you burn fuel in the mission and that change?
I'd actually like to have Michael Appleswag answer that question for you.
Yeah, so the longitudinal fuel tanks, the fuel excursion diagram we developed in preliminary design did show a shift in the center of gravity as it goes forward. So the aircraft becomes more stable in pitch as fuel is burned, which is unconventional with most other swept aircraft. So in fact, the aircraft will become more stable. It would not reach neutral stability or just before neutral stability at once all the tanks are burned. And the fuel burn order was also optimized to minimize this overall shift in CG.
Okay, would you plan any sort of mitigations to prevent sloshing or movement of the mass of the fuel?
Yes, so in our fuel estimations, predictions, we did account for baffles inside the tanks, and there are figures of merit that are used for bladders and dividing the fuel tanks to minimize the amount of sloshing.
Great, and then my only comment was, you had good sections in the slides that summed up your compliance to the requirements, but one thing that's really nice is when your design reviews are sort of standalone and they don't need the presenter to explain the detail slides. So it's good just to put, if you're making a point, go ahead and put that point on the slide and, point an arrow to the part of the curve that makes your point. That way, your work can, get handed around and somebody can get your entire messaging without you there.
Yes, thank you.
But thanks, great job.
I'm Roger Bartlett. I'm also work for Raytheon Missile Systems. I've been there quite a while, done various things. Right now I'm a lead systems engineer for a very large missile program. I won't say. But anyway, so I would like to ask a couple of questions more on the lines of requirements and conceptual design. So the obvious thing that stands out right away when you look at this is the forward swept wing. So could someone comment a little bit more, I guess I missed that, exactly what your specific requirement drove the forward swept wing?
Yes, sir. I'd actually like to pass that question off to Andrew Bolda.
So when designing this aircraft, we determined that the most constraining factors was the ability to supercruise and sustain the 9G maneuver. The F-14 Tomcat was the latest interceptor, and that implemented a variable sweep in order to reach its intercept velocities. However, it didn't have the load capabilities that we needed. So we needed to figure out how to basically get the best of both worlds to supercruise and sustain the load. So we looked into the forward swept technology and realized that it would be possible to complete the mission with that design.
All right. So on other requirements, I know it's probably out of the scope of your effort, but I'm wondering what drove the armament requirement?
So the armament requirement was actually specified to us by the RFP. It was required to have 4 missiles on board, 2 radar and 2 heat-seeking, and as well as a 20mm gun with 200 rounds.
Okay. And kind of follow up on requirements, was there any RCS requirement stated?
No, there was no.
Okay. Just as a way of, as a recommendation, it doesn't hurt sometimes to mention what requirements that you know were purposely omitted and that you didn't ignore them, but no, your customer didn't specify. It's good to tell the customer that you recognize that they omitted the requirement, just in case they omitted something.
Thank you.
Then maybe one more question on structural analysis. So what I couldn't tell from that is whether you had a dynamic load factor or a factor of safety built into your numbers, and since you had, for the forward spar, since it had a really small margin, was there any desire to optimize that?
Yes, and I'd like to actually have our structural analyst answer that question, Parker Phillips.
So there was a factor of safety of 1.5 built into the initial calculations. There was also a lot of worst case scenario built into not having any of the structural weight factoring into the configuration, or not having any of the fuel weight was considered. So none of those things which would technically help the structures by having a lift weight going in the opposite direction of the lift, or an actual weight going in the opposite direction of the lift. So none of that was considered, which is why the 128 is relatively acceptable. It would be ideal to add a third spar, a partial span third spar. The main portion of the air elastic tailoring takes place at the tip of the wings, and so it's idealized to have 1 to 2 spars there. However, it would be prudent to add a third partial span spar through the strakes or in between the 2 spars already there, in order to increase the bending resistance at the attachment point where it's most strong.
Just a follow-up question on that. Is there any need for a knockdown factor for temperature on in terms of your material allowables?
Not to my knowledge, but I didn't do any specific research into that.
Okay. All right, thank you. So overall, I think this is an excellent presentation. Thanks.
Hey, great job, guys. My name's Kenny Young. I'm just sitting here for the morning. So I'm down at Boeing Mesa. I'm a product review engineering manager. And previously to that point, I was product review engineer, or also known as liaison engineering. And I also have been in the same situation as you guys, albeit more years than I can dare say. So let's go on to your material selection, slide 19. Again, great job. Walk me through how you guys came up with your material selections.
Again, I would like to defer that question to Parker Phillips.
So the aluminum, to start with, was selected because it's a very common product in aerospace. It has a light weight but maintains a relatively high strength. And so that was utilized for the majority of the aircraft. It's also relatively cheap, which helps bring down the cost of our aircraft. However, because of the flaws of wing design and the lack and the crucial components of the wing spars, titanium was utilized has a higher strength to it. However, it is lighter than steel, which therefore, that's why steel was not selected for that option. And the carbon fiber was utilized because we need to have a non-symmetric layup of our wings, and because we need to implement the aeroelastic tailoring effects, which cause, as the wing is loaded under a lift load, it causes the tips of the wings, the leading edge of the tip of the wings, to curl down in order to prevent torque failure, essentially, on the tip of the wings, aerodynamic effects like we're.
So I noticed on your spars, you picked tie. Did you do a cost-benefit analysis choosing between tie versus, say, some 7 series aluminum, or you just said, I like tie because that sounds pretty and exotic and it costs a lot of money?
It does cost a lot of money, which is part of the desire to add a third spar, as it is it'll help reduce the amount of actual material required. It was more of we really do require the strength of the tie. It's not so much specifically, just sounds cool, but it does. We do really require that type of material versus 7 series aluminum.
Okay, fair enough. Let's go on to slide 22. Looking at your margin on your forward spar, there's a couple numbers that stood out to me on this. You've got pretty small margin in terms of your material limit versus what your ANSYS model predicts. Where's your margin for repairability for fleet? You're right on that line right there. So where's your damage allowables?
That was not covered in the scope of the project.
Okay.
We were just analyzing to ensure that it would fit within material properties for this project.
So just something to be thinking. In any type of platform that sees excessive loading, is in austere environments, especially hot, wet, a lot of times you're going to run into conditions that need repair. And when you have something so optimized down to the margin here, you don't leave a lot of room for the operators to keep their aircraft in service, okay? So just the learning point. The second thing that stood out to me was your wing skin shears. So you have a material limit of 26 KSI, your ANSYS model says 3 KSI. How did you come up with those numbers?
A lot of that is due to the loading which was applied to the ANSYS model. It's applied in a direct point load to the spars themselves, and therefore doesn't essentially translate particularly much to the skin loading. I believe if it were analyzed further with a distributed load over the wing itself and over the surface of the skin, then it would change and have a higher skin loading.
I guess maybe rephrase that question. How did you come up with your material limit of 26 KSI for your allowable?
26 KSI was used from a previous project where kind of a standard symmetric carbon fiber layout. And so it was a very much an approximation and an assumption. But due to limitations on time and scope of money and materials and facilities here at Amarillo, we were not able to design any type of actual aeroelastic tailoring. And so therefore it was just an assumption based on previous layups.
Okay. Overall, again, good project. My previous experience with our other teams, the fighter roles tend to be pretty ominous and tedious as well, but you guys did a very good job in terms of design, so good job.
Okay, I'm Jeff Jansen. I work at Honeywell Aerospace in Phoenix. My area of responsibility is for propulsion and auxiliary power unit equipment, mostly on government programs. First of all, I gotta say that Boeing and Lockheed Martin probably aren't very happy with you guys right now. You're giving them some tough competition, so great job. Let's see, just a comment about requirements and so forth. An omission of requirements, just to reiterate, for example, the total range of the aircraft and the comparison when you talked about 200 nautical miles at Mach 1.3. It's not a question, just clarification around how that would stack up against, let's say, against the F-22. Okay, so no question there, just clarification about what the requirements are. You met the requirements. Obviously, in reality, since Lockheed Martin's upset, they're going to point out that they have some different capabilities that maybe weren't necessarily requirements for your design. Okay. Let's see. On page 29, you showed a brilliant video. You showed your parts, everything just assembled together brilliantly. It was so easy, and I'd like to ask the question whether or not it was really that easy. Did you experience any challenges with manufacturing and assembly of your model?
So the design was made so that everything could be assembled very simply. But when we actually did get the model parts cut with the water jet, some discrepancies were there in the accuracy of the cuts. So a lot of the fitting was very time consuming in order to get the slots to line up with the plastic printed parts, along with the complicated bends in our U-brackets and the lining up of the actual spars within the hole that was designed in the 3D printed parts. So there was quite a bit of time that was taken in assembling the entire model, but once it was completed, it was very simple to interchange the parts during the wind tunnel testing procedures.
Okay, great. The point being that you can design the greatest performing aircraft equipment in the world, but if you can't manufacture it, it's not worth much. So design for manufacturability is one of those trade-offs you always want to think about, okay? Page 36, just a clarification on the curves here. You have the solid line that says predicted, and then you're talking about full configuration and others. So is the predicted comparing to the full configuration? Is that how I read this?
Yes, that's correct.
Okay, just to clarify, I want to clarify because I see one predicted line implies you're comparing it against different things. So, but you just did one analytical model for the full configuration, right? You didn't, okay.
Yes, that's correct.
Okay, I think just two more here on page 50. It says you moved the wing spar aft by 9/10 of an inch. Did I understand that correctly?
Yes.
Could you tell again, what was the constraint? In other words, 9/10 of an inch, was that the optimal But you would have made the move to aft, or was there some other constraint, like a physical constraint? I think that's what you said.
No, I'm gonna like to pass that off to Jonathan Swisgood.
Okay.
So the constraint on how far we could move the wing aft was actually budget, because we were not allowed to reprint the fuselage of the model. So we had to use the same attachment points or re-drill attachment points, because we decided that remaking attachment points would probably not work out that well. We had to keep the same ones, which meant the wing spar had to go in the same slot.
Okay, well,
Yeah.
was that optimum, 9/10 of an inch wasn't necessarily optimum from a performance?
No, not from a performance standpoint.
Okay, what was the optimum? Did you
The
guys-
optimum would have been to move it aft on the model, I think over 3.5 feet. It would have been a lot because we wanted to get, or on the full scale aircraft, because our optimum point that we would want the static margin to be would be around 0.01, and the static margin for the model ended up being 0.27, I believe.
The constraints are a reality, right?
Yes.
Last question. If you had to do it all over again, would you still select the forward swept wing? Why or why not?
I believe we would still select the forward swept wing. When we decided to pick the forward swept wing, we were looking at some pretty advanced technologies, and we were confident that this design was the best we could have picked, and I would do it over again. I think that is the same feeling throughout our team.
Okay, well, thanks for being ambitious, and we'll talk about foldable wings for the aircraft carrier out in the hall. Thank you.
Might have stolen one of my questions. So my name is Connor Warren. I do rocket propulsion in California. I'll just start off by saying, good job, you guys. You guys, looks like actually got pretty far. You guys managed to get through the first iteration and into the second iteration, which is always a good sign. So I'm going to go as quickly as I can because we only have a few minutes here. So first question, which FAA team did you guys compare to? When you guys were talking about in the beginning, you're comparing to the FA-18. Do you know which version?
Yes, we were comparing it to the F-18 Super Hornet, which is the updated version for that aircraft.
Okay, just want to make sure of that because that's a difference that can be overlooked.
Okay.
So, second question, for the F-135 engine, I believe, can that engine operate in sea conditions?
I'd like to pass that on to Andrew Bull to give a better response.
Well, we believe because this engine's implemented in the current F-35 technology that Pratt & Whitney has designed for that consideration. However, we just chose to pick an engine that was in production already.
Okay. You may have said that and I may have just missed it. It was just something I want to double check in because that's something that's overlooked sometimes when you're operating at seas, that you're dealing with a lot of additional salt that will really wear out your engine. Slide 22, please. Not to jump on the bandwagon here, but just something that might help you. Was there a factor of safety used for these calculations?
Yes, there was. There's a factor of safety of 1.5 used for these.
Okay, it might have just helped to display that, just to show that, yes, we thought about it, this is how much margin we gave ourselves. It just helps communicate that it was included.
Thank you.
So slide 29, manufacturing question. I guess we'll look at the secondary screen. Did you try to fill in the voids when you put it all together with anything to try to smooth the skin out?
Yeah, we did. We used modeling clay
Okay.
in order to fill all the voids and make sure that everything was smooth.
Okay, because that was something I was a little curious about, because I was just thinking, if you put it in a wind tunnel, you may be catching on those edges, but if you use modeling clay, that would help you out. By the way, that was an awesome model.
Thank you.
Let's go to slide 32A. That'll be my last one. So, how did you guys, for your configurations, how did you ensure that your mounting surfaces did not interfere with your model when you were testing it? Because you said you were trying to isolate your configurations. So is there any way you guys checked to make sure that those mounting surfaces did not interfere?
Yeah, we did. We actually conducted a tear test for the mounting surface in order to extract that data from our calculations.
Okay, just wanted to make sure. Other than that, great presentation. Thank you guys.
Thank you very much.
I told these guys that I would not ask any questions because I know where all the hard ones are. But I can't help it, I'm sorry. Go to 69B. Ship 2 is way out of position. That's all I got, thanks guys.